Okay. What I'm doing now is uploading well, I just uploaded the latest the version of the practice final exam and solution. Although what's rather infuriating is that I can see in my FTP client that today's versions have been uploaded, but um, Firefox doesn't want to open that version, so apparently I have to play hardball and like clean out the cache, blah blah blah. Let's see if that works. So I don't want someone saying, "Oh, it's not the old version." Well, the new version's there. Um, oh, this is so maddening. What is wrong with you? Okay. Because it has 8 regular problems and then 15 lightning round questions, of which only 10 need to be answered. Okay. So I had to suspend recording for a little bit to deal with that. But um, expect an email with the practice final exam and solution. And next week we can spend some time going over that. Now, today, just continuing with Laplace transforms. Last time I did an example where we had the second order equation, constant coefficients, homogeneous, and distinct real roots. So now we're going to look at other cases, complex roots, repeated roots, non-homogeneous. So that should pretty much cover the kind of cases that you can expect to see, like on a test. Well, at least from this section, and then we have still a couple more sections to do. Okay, so. Now in the notes I have just, for the most part, just some abstract cases. What I'll do here is fill in specific numbers. This is 6.2 in the text, 5.2 in notes. So for the first example, let's see. All right, so I just made a distance value problem for conditions that I want. First thing you do is you take the Laplace transform of the equation. Using these rules, it's a Laplace transform of a derivative is s times the transform of your original function, subtract off the value at t equals 0. And similarly, Laplace transform of the second derivative is s squared. So as you differentiate, that means the number factor of s. And then minus y prime of 0 minus s y of 0. Okay. Now, so we go ahead and apply those up here. And so I'm going to write down as we go. These are rules that you need to, and you're going to have a table of Laplace transforms during the test. But these are ones that should be more fresh in your mind, and certain other ones that I'll write down as we need them. Okay, so second derivative, so we're going to have s squared y hat minus y prime, which is minus 2, minus s times y of 0, which is 1. So that's second derivative, plus 4 times transform of first derivative, so that would be s y hat, minus y of 0, which is 1, and then plus 4 y hat is 0. Now, keep in mind, you're really transforming both sides of the equation. Now, in this case, right side is 0, so you're going to get 0. But for an inhomogeneous equation, as you'll see later, you would take the transform of this side too. And that will be taken into account when you solve for y hat of s. So now that that's done, the next step is group everything in a way that lets you solve for y hat of s. Okay. So everything involving y hat on the left side, everything else to the other side. So you're going to have s squared y hat plus 4s y hat plus 4 y hat. And then everything else we move. So we have, let's see, there's an s that moves to the other side. And then we have, on the left side, there's plus 2 and minus 4. So minus 2, but that becomes a plus 2 when moved over.
Wouldn't it be a minus 2? Because the negatives cancel, don't they?
Yeah, minus 2 on this side. Yeah, we have plus 2, minus 4, but then I take that and move it over.
Sorry, I missed the minus 4.
All right, but at least you're looking to see if I messed up, because I'm going to mess up. So, just not yet. Okay, next. We're going to factor out y hat of s on the left side. So you can readily isolate it. So we have y hat, and you get s squared plus 4s plus 4 is equal to, oh wow, I blew this so badly. No, okay. I just literally made up these numbers. I happen to choose numbers that are going to make the problem, I should say, uninterestingly easy. And I think that's not good for you guys because you don't see what the possibilities are. So I just need to change, okay. I'll change this to a 2. So we have all right, so then I have plus 2 minus 8, so minus 6, it becomes a plus 6. And then we have 2s. Okay, so 2s plus 6. All right. Wow. You'll see what I mean in a moment, though. And that's equal, okay. And okay, and now we can just isolate y hat of s. All right, so we have 2s plus 3 over s squared plus 4s plus 4. Okay.
Couldn't you reduce that to... Oh, wait, never mind.
Okay. Well, this takes me to what the next step is anyway. Factor the denominator as much as you can. How does that factor?
S plus 2. S plus 2.
Yeah. That's plus 2 squared. And this is why my other choice of initial data is not going to lead to the most interesting case, because I'd have s plus 2, which would cancel with one of those down below and give me like a real simple solution. Like, no. I'm trying to be one of those professors who just gives the simplest example in class and then hits you with something super hard to test. Well, unless it's for bonus. But okay. Now, the next step After that is partial fractions. Now, so what happens in this case, so we have a repeated root case, so that gives us an idea of what our final solution is going to look like, except for constants. It's no accident that this is the same as what you would see from the characteristic equation. And that's something that happens in general, because orders of differentiation are still being replaced with powers of now s rather than r or lambda. Same idea. Okay. Now, so we have so what is the proper form? This is something that students mess up sometimes when you have a repeat linear factor like this. What form are we looking for partial fractions on this?
A over s plus 2 and then plus b over s plus 2 squared.
Yeah, or s plus 2 squared. What some people do is just write s plus 2 again. It's like, nah, that doesn't cover everything. Okay, so now what you can do is, and this is what I messed up last time, we multiply through by the denominator. All right, so we're going to get a s plus 2, and then we're going to get just b over here. Okay, what's a convenient way to isolate either of these coefficients, a or b? Yeah, plug in s equal minus 2. Really, you can plug in any two values of s, and you get a system of two equations, two unknowns. But the most convenient values of s to substitute in are the ones that make either of these denominators 0. Now it's best for like when you distinct linear factors, but it helps here too. Okay, so we have minus 2, so we're going to have minus 1 is equal to, so this goes away, and you're left with b. So b is minus 2.
Should it be 2? That's negative 2 plus 3.
Oh. God. Well, I did tell you I was going to mess up. Okay. Apparently I'm cursed with partial fractions. Okay. And now what you can do is substitute. There's no other super convenient value of s, but you can just pick any other one. So what I always do in this case is choose s equals 0. So you have 6 on the left-hand side, and then 2a, and then b is equal to 2. So a is 2. Right? Okay. All right, so now we have our partial fraction decomposition. Okay. Any questions so far? Awesome. Thank you. Okay. Now, for the final step, we invert the transform. And so the rules that you would use in this case, there are two that are really put together. So the Laplace transform of t to the n is n factorial over s to the n plus 1. And I think you're actually going to be using these rules in reverse. So there's a lot of pattern matching going on here, which you need to be very careful. And then the other is that e to the at f of t is equal to Laplace transform from that is the Laplace transform of f, and the exponential causes a shift. Okay. So what you could do is put these two rules together, and what that tells you is that so really I want to go backwards. So what I have here in both cases, I have some constant, and that's just handled for linearity. But what do you have? Like 1 over s plus 2 or 1 over s plus 2 squared. So you have a shifted linear factor. So putting these two rules together, you have this, and so can anyone tell me, again, using these two together, since this is a shift of this, what should I put here? So,
Would it be f of t to the n?
no.
E to the AT.
Yeah, EVAT.
Yeah.
What?
F.
Okay, well, what is f in this case?
T to the
Yes, t to the f. All right. Okay. So what you have in your transform is this, and you're going to be backtracking to that. Okay. So you could say, for instance, fancy L inverse of this is this. So in this case, you want the so y of t. Your solution to the original problem is inverse transform of what do you have there? 2 over s plus 2 plus 2 over s plus 2 squared. So by linearity, you can handle these terms individually and pull out constants, just like with differentiation or integration. Okay. So now, if we go ahead and fit what you have here to this right-hand side, then you know what to go back to. So, okay, we're going to have 2 times something from the first term, and 2 times something from the second term. So now it's up to you guys to fill in the blank. What is A in this case?
2.
No,
Negative
close.
2.
Negative 2. Yeah, because it's S minus A down here, but we have a plus 2. All right, so A is minus 2. So what do you have to do in each case when you're fitting this to this? All right, A is handled. You have to identify the proper value of n in each case, and then you can write down your inverse transform. So what should it be for the first term? Sorry, what?
0.
Well, okay, n is 0 for a first term. So now you just go ahead and so this
It is 0.
n is 0,
And it's 0, but 0 factorial is 1.
right? So we're inverse transforming this, so we need to go back to here. So this is your form.
So we have to go to there.
Yes. And now that we have all the particulars, we know what A is, we know what n is.
So it would be e to
E
the
to
negative
the
2t.
2t times t. No.
Yeah.
Yeah.
Times 2. No.
No,
Times
it's
2,
0.
1.
Yeah.
It's just 1.
Yes. Because n is 0 for this first term. So we just have 1. Okay, but what about the second term? Or this one?
N is
Yeah.
1.
Yes. So
E to the negative 2t.
t. Yeah, now the t creeps in because of n being 1. And that's it. You're done. And it's kind of expected because you look at your characteristic equation, you have s squared plus 4s plus 4, that's a perfect square. So we have a repeated root. So it's no surprise that that kind of term would show up. Okay.
So that's all we do.
Yeah.
Give us the forms.
Yeah, these, you'll have a sheet that's a photocopy from a textbook that has all these and other ones. Okay. Is there any questions about the process? And the process will proceed exactly the same way for any Laplace transform problem. The thing that's going to be different is which rules you'll be using, because of whatever you happen to get for y hat of s. Because so this next example, we're going to need different rules than what we needed for this one. Then when we get to non-homogeneous, that can make things more interesting. Also, one thing you can do quite easily with Laplace transforms that you can't do using the previous methods is suppose you have a right-hand side, your g of t, that is discontinuous. So there's like a jump in it. So you have like some piecewise defined function. Laplace transforms can be used to handle that. Well, I wouldn't say it's easy, definitely not. But at least it's doable, unlike with the other methods. Okay. So now step through another. That will bring different rules into the picture. Okay. So I have y double prime plus 2y prime plus, let's see, plus 5. 0. And hopefully whatever addition values I pick won't cause difficulties. Okay.
So you have to have initial conditions.
Yeah, because otherwise, what would happen is your solution would be specified in terms of like these unknown values y naught and z naught. It makes the algebra more painful. So yeah, here for a test, actually, to your advantage for me to specify initial conditions, unlike the other ones, where it's better to ask for a general solution. Okay, so what will happen? So I'm going to go through the first steps a little more quickly, just because it's exactly the same thing as before. So we have s squared y hat minus y prime of 0 minus sy of 0 plus 2 sy hat minus y of 0 plus 5, whoops, should be y hat, y there. We're not doing an inhomogeneous equation yet. Okay, and then grouping everything, so we have s squared plus 2s plus 5 y hat, and then everything else gets grouped together, so we have minus s minus 3 minus 5, okay, so equal to s plus 5. But I have to remove it to the other side. Be sure to check my algebra there because I can't be trusted. And now our transform of our solution is s plus 5 over s squared plus 2s plus 5. Okay, now, that's what I get for having 5 in my problem. But you can't tell it from an s unless I'm very careful. Okay. All right. Now, so normally, like in the last example, the next step would be, okay, go ahead and factor this. This does not factor nicely, because if you were to try quadratic formula on it, you would find it has complex roots. So the roots of this, if you were to apply quadratic formula, would be minus 1 plus or minus 2i. Now, so when that happens, the best thing to do is write it in a square completed, a square completed form. So this would be the same as s plus 1 squared plus 4, which I'm going to write as 2 squared. And it's to your advantage to write this as a sum of squares like this. So what will happen is, here you have minus the real part. So if you go ahead and figure out the roots like you always do, minus the real part is what goes here. That's the plus 1. And then the imaginary part goes here, and that has to be squared. So if you know the complex roots, you know you can just go ahead and write it in that form. Okay. All right. Now, the next thing you want to do is write this in the form where you can fit it to the certain rules that you're going to need. I'm going to go ahead and write down the rules now, because I think, oh, we should do partial fractions. But it's actually not the best way to go here. So these rules are completely different. Well, okay, one we still need from the last example is one involving an exponential. But these other two are a result of having this irreducible quadratic here. So transform of cosine bt is equal to s over s squared plus b squared. And transform of sine bt is equal to b over s squared plus b squared. And we can see that in the denominator of both, we have a sum of squares, and we have a sum of squares down here. But it's shifted. Instead of s squared, is s plus 1 squared. And that's why the rule for shifting needs to come into play.
Does that say last fraction? What does that say?
B over s squared plus b squared. Well, b is a constant, whatever constant's in front of a t in your sign. Okay. Okay.
So it's not the same B on the bottom.
These are the same. Yeah. Yeah. So whatever you have here goes here. And similarly for cosine, so cosine you have it only in the denominator with an s up top. So in fact, oh, never mind. Okay, I was about to say something wrong. Now, we need to get this into a form where we can readily apply these two rules. But first, let's combine them with this. So it can actually be helpful not just to use the rules as they're given to you, like on that sheet, but to combine them to have rules that will be more directly applicable to your situation. So if we put these two together, what we have is instead of s, if we have s minus a up top, and then we have s minus a squared plus b squared, then putting these two rules together, what should I fill in here? Kind of like the last problem. Wait, what? No. There is an exponential. Keep in mind how the exponential looks in the final result over here. So the question is, what is your A? What is your F? Or at least okay, let's not think about that for now. But so
e to the at
yes,
cosine bt.
cosine bt. So the idea is this is f hat of s minus a, where f hat of s is the unshifted version of this, s over s squared plus b squared. And the thing is, the shifting needs to happen consistently throughout. And so from here, if you unshift this, then you get f hat, and from there you know what f is, cosine. And because you're applying this rule, where you're dealing with a shifted function, that just means after you have this function, you just multiply by an exponential, plain exponential, e to the at. So that's something that you need to build up to be a reflex for you when you're working these kind of problems, like on a test. If you have a Laplace transform that is a shift of a known transform, work out the inverse transform of the unshifted version, so in this case cosine dt, and then go ahead and fill that in, and then bam, put the exponential there. And the exponential comes from whatever the shift was. So for this other case, what would this go back to? E to the AT sine bt. Okay. This is the only place where S appears, so that's the only place the shift appears too. So now if you can fit what we have here to these rules, then you can just go ahead and invert and write down your solution. But to make that happen, there's a little algebraic manipulation that needs to happen first. Any questions just to this point? Like where those rules come from? This is a pattern matching part that's essential. So the thought process to go through is recognize when a function is just a shift. So you have f hat of s minus a. So mentally, you go from that and figure out, well, from there, what is it the shift of? So you go back from there to the unshifted version.
You give us the first three, right?
Yeah, all these rules will be given.
And then the last two we have to figure out.
Right. Or you can try to memorize them before you go into the test. But they can also be put together from these that you'll have. Okay, so then you invert the unshifted form. F hat of s goes to little f of t. And then slap your exponential in there. So that's the way this has to work. Okay.
So theoretically, you could also do the combine the cosine bt and the sine bt.
By combining, you mean like
what we did here with the either the exponential and the cosine bt.
okay.
Would you be
I don't-
taking the transform of cosine bt, sine bt?
Oh, okay. You mean like you think? I'm not clear what you mean by combine. Like a very linear combination of them, or multiplied, or
Like how we did when we came to how we got to the that transform. Could you do that with cosine bt and sine bt as well?
okay.
It's possible for if our root is 0, first root is 0.
Oh.
Instead of negative 1, the root is 0.
Oh, in that case, then there's no shift. You would have only a cosine or a sine. Okay. So what you're saying is, in contrast to what was done here, where this rule was combined with this one, are you saying like combining these two?
Yeah.
All right. So in that case, because there's a really, well, for one thing, the depending on what way they're combined, really the only combination that works in a straightforward way is a linear combination, adding and subtracting, because the transform of a product is not the product of the transforms. There's a separate rule for that. And also, we don't have a rule for composition of functions. So there's no meaningful combination for which the same thing would occur, just because we don't have that kind of pattern among our rules, whereas here we do. but at least you won't need that anyway. Okay, so now that we have these rules, we're going to apply that to this. Okay, so the transform currently is s plus 5 over s plus 1 squared plus 2 squared. So what you need to do is, like in the rule for exponential times a cosine, you have s minus a up top, s minus a squared down below. What is a in this case, and what is b? Based on this transform.
Negative 5.
Now look to the denominator, only denominator.
Negative 1.
Yeah, -1, and yeah. Okay, so we're looking at e to the minus t cosine 2t sine 2t. Now to get this doesn't fit either one of those rules yet. So we do a little trickery. I write s plus 5 as s plus 1 plus 4. And the reason I do that is I really want an s plus 1. So now you can break this up. So that will fit one of the rules. And then for the other rule, you have, you really want 2 up top, but you have 4. So go ahead and put 2 here, and then the other 2 will sit out here. That way, each actual fraction will exactly match one of the rules.
So you put a 2 there to make up for the 4.
Yes. So whatever constant you have here, what you can do, actually, if you just go ahead and multiply and divide by b, whatever b is, then you can force b to be up here. Everything else goes off to the side. So now, I can inverse transform this, and what will I have? Using the new rules over there. Yeah. All right, and you're done. Okay. So this is all one big pattern matching exercise, trying to get what you have to fit the patterns that you see in these rules. And it's something that can be a little tricky, as you've seen in cases like this, to get that exact match. Okay. Now, unfortunately, sorry, attendants, please pass around the room quickly. Yes.
How did you get A and B?
A is because it's fitting this situation. S or B, whichever one. It's really about the denominator. S minus A squared plus B squared. So you match this to this and this to this. Figure out A and B. Okay. Sorry, I didn't realize for the last 4 minutes to take attendance, so please sign quickly and pass quickly. Yes.
So we use the general solution for like the average ordinary second order.
Yeah, that's what's going to come up. Quick, keep moving. Yeah. I'm going to nag everyone in the last 4 minutes. Okay, won't be able to cover anything else. Okay, now the. Okay, and now my pages are all missing. Okay. I won't be able to finish this one, but I can continue it on Friday. So y double prime minus 2y prime plus y is equal to e to the 2t. Y is 0 is 1, y prime is 0 is minus 1. And the left side, it works out exactly the same way. I won't even, and this is all in the notes too. S squared minus 2s plus 1 y hat. And then the other terms that come from the initial conditions turn out to be plus 3 minus s. And then what you have to do is use the rule for the right side. Use the rule that the Laplace transform of e to the at f of t is equal to f hat of s minus a. So in this case, a is 2 because we have an exponential. And here we have an implied f of t is equal to 1. So 1 is what you're transforming. But the Laplace transform of 1 is 1 over s. So the transform of e to the 2t is this function shifted by 2 to the right. So it's 1 over s minus 2. So that is the Laplace transform of e to the 2t. Now we saw that in the first example from today. In that case, we were working backwards, and now we're working forwards. So now, if I were to solve for y hat of s, well, I'm going to have 1 over s minus 2. That was already there on the right side. These terms move over to the right side, so I have s minus 3 now. And all of that's divided by s squared minus 2s plus 1. So now what I want to do, and I have 1 minute, it's best to break this up into 2 fractions. So we have 1 over s minus 2, and then the denominator here is s minus 1 squared. And then the other fraction is s minus 3 over s minus 1 squared. So that is what has to be inverted. And this is what makes non-homogeneous equations especially painful, because you got to do partial fractions twice now. If you work on these separately, and then invert from there. Okay. Now, or what you can do, actually, no, that's wrong. You can do that. But the best thing to do is take this, put over a common denominator. This is what I get for not looking at my notes first. And then you only have to apply partial fractions once, but to the largest fraction that you could have. So we'll continue with that on Friday. Be sure to sign a seat, which better be moving around the room before you leave. Please tell me it is. Done. Okay. Thank you for being so efficient. Bye.